Okay, and so that's 7. Good, yeah, that does match. Okay, and then let's go to the 16. That looks like about a, I'll call it a 6-4. Now let's go to 17. And that looks like about a, let's see, that'd be a 5-8. Let's go to 18. That would be about a, let's see, that would be 5-3. Let's go to 19. Let's call that a 4-9. So 4.9. And then let's go to 20. Oops, I keep bumping that wire. I shouldn't do that. 4.5. 4.5. Let's go to a 24. I'll call that a 3-3. . 28 would be right there. Let's call that a 2-5. Really low value. See, we're even lower than that one. Where are we? So out to 32. Let's call that a 2.0 or 0. I guess O is a letter, not a number. Oh, and I lost track. Well, where am I? 36. 36 right there. 1 point, let's call it 8. Let's go to 40. 1.5. Let's go to 44. 1.3. 48. Well, it's not jumping around. So that's good. Usually in a big class, we just get a mess at this time. So I hope the pattern's still going good, because that looks like about a 1. I've got a 1.1, 1.2. Yeah, let me call it 1.2. 1.0, 0. And 56. I'm going to call that a 1.0 also. And last one of our raw data. It's just under, let's call it a 0.9. So 0.9. All right, we got the raw data. All right, so I'm hoping the lab kind of made sense to you, and I'll say it again. Here it was the big picture. The big picture was to see how the electric field changed at different locations, and also with different charges. And so we had a lot of charge, 3 times the last one, and the second time we did it was 2 times the last one. So we have these multiples, because then here's what you need to do before you turn all this in. Let me just double check. I said there wasn't a set of discussion questions, and there's not, except on step 14 it does say, now that you've made your graphs, what can you conclude? All right, so here's what you want to do. There's really 2 graphs you're going to be making, and each of those graphs have the 3 plots. You're asked to do this, and I'll say it again. Use whatever program you want. I'll just refer to graphical analysis, since that's what we provide free of charge on our virtual desktop, and it's really easy to use. And I pause a little bit because I said you actually use when you do physics 121, but I hesitate. Thank you. I hesitate with saying that because for the first time, as many of you know, half of you took Physics 121 last semester with Doug. So I'm going to confirm and see if you guys did the graphical analysis. But I'm pretty sure you did. Actually, Ron, you might know. Yeah, pretty sure. Ron's saying, yeah, he thinks you guys did. Okay, good. So because you're in here and you're doing all that Logger Pro equipment, I'm going to go with that and then find out and then send you an email or whatever how to get to the Logger Pro if need be. But if you get Logger Pro or Sheets or Excel, here's what you want to do. Make a graph. Okay, and the first graph is going to look like this. You are to plot the electric field as a function of position. Okay, and yeah, so should I, there's a bar in the way here? Okay, I'll move it over here a little bit. But I do want to give myself enough space for two of them. All right, so your first graph will look like this. So here's the electric field versus position. And hopefully it'll look something like this. In our case, we would be starting at a position of 0.1 meters. So if we put position in meters and the electric field in newtons per coulomb. And looking at our data, that's going to be way up here at 49. And so the biggest one we will have is a 49. But hopefully your data will begin to look like something that has that inverse relationship, the inverse of the square. Also plot the second experiment we did, which as you can see started at 32, and so hopefully your data will look something like that until you can kind of just do a connect the dots here. You don't have to do a curve fit. Again, we're going to do something better here in just a moment. So no point in doing a curve fit here. Just kind of eyeball the pattern. And then, of course, the third one we just did, hopefully, will also show the 1 over r squared value. So that's what you're supposed to be learning in here, is that there is this decrease of the electric field as you get further and further away from this charge object. It's a 1 over r squared. But you can then also see that it's proportional to the charges, because this one is 3 times bigger than the first one, and this second one is 2 times bigger than the first one. But I think you can see it even better with the next graph we're going to do. This next graph shows it a little bit better, and it's something we like to do in science and engineering. Instead of having a complicated plot, we have a complicated axis. Here's what I mean by that. You are going to then plot the electric field versus 1 over the distance squared. So in graphical analysis, you're going to have to make a new column, and that new column, instead of being R, would be a calculated column. And of course your computer would probably put it right about in this spot, and it would be 1 over r squared. And so this is what I mean by saying we're going to change our graph from being a complicated graph and a simple axis to a complicated axis. And so 1 over r squared is like, oh wait, that's just something weird to plot. But watch what it's saying here. Why? If I were to write out Coulomb's law up here, and I would write it in this form, you can see that it's saying that the electric field is proportional to 1 over r squared. That's what we're trying to prove. And when it's proportional to 1 over r squared, it would be a straight line. So what I'm hoping here is you will get something that maybe looks like this. See, you get a simple plot, a nice straight line. And of course yours is probably a little curvy because, you know, our equipment's not the most accurate in the world, and your lab partner probably messed up making the measurements here. So that is hopefully roughly a straight line. And maybe I shouldn't have put that little curvy thing. I probably should have done something more like this, that maybe your data looks a little curvy, like that. But hopefully it is close enough to looking like a straight line, because go ahead then and do a curve fit, a linear curve fit, and put in the straight line. Because here's what this is saying. This is saying every time you see a straight line, this is saying this axis, electric field, straight line, is proportional to 1 over r squared. So that's our proof, if you will. That's what we will hopefully see. And of course, then your second piece of data will hopefully look like this, and your third one will hopefully look like this. And if you look at the slope, and slope, coming back over here, the slope would be this number. So in other words, we're plotting this on the x-axis, and so this number here would be the slope. And notice that number is related to how much charge. And so if you see this big slope about 3 times the slope of the first one, and the second one here about 2 times the slope of the first one, you are then also proving that the electric field is proportional to the charge. And so we are hopefully collecting data, what I would say getting evidence, physical evidence. Empirical evidence is the fancy word we like to use in science. You now have empirical evidence that these two things are true. Number one, the electric field decreases in proportional to r squared, 1 over r squared. The inverse square law of electricity, the title of the lab. And the second thing this graph is proving is that the field is proportional to the amount of charge on the sphere. That wasn't in the title, but that is what our data would be showing. So that's why I said back here, you don't have to do a curve fit on this one, just kind of get the overall pattern. We're not going to draw any conclusions from this. This is really just a graph for you to make you feel comfortable, because as a beginning scientist and a beginning engineer, you're used to making simple axes, and then if it's a complicated graph, so what? Probably back in 7th and 8th grade, you had simple axes and simple plots. You just had straight lines, and maybe at most you had a parabola. Now that you're more advanced, you probably have still simple axes and complicated graphs. And now we're trying to change that one more step away from high school and into college here, and say, let's do this. Let's make our axes complicated so that our graphs are then simple. And so this is our proof. And so that's what you're going to be turning in. This page, this graph, and this table. And then, of course, the answer to only one question that they ask. They don't even put it in a discussion. It's just right there in step 14. It says, now that you've done this graph at the end, can you draw any conclusions? And I hope I didn't give it away too much, because I did. I wanted to make sure you didn't see it. So I'm going to say it one more time. When you get this graph, these are the 2 conclusions that you will hopefully get from your data. That the electric field is directly proportional to the inverse of the square, and also the electric field, because of the slope here, is proportional to the charge. That's not only Coulomb's law, but it's also what we're learning this week for Gauss's law, that it actually follows that pattern even if you don't have a point, as long as you have a sphere that is symmetric. And of course, in our case, it's a conductor, it would be symmetric on the surface. But if we had an insulator, a uniformly charged insulator, then it would be symmetric within the whole volume of the ball. All right, so that's the end of the video lab for this week. Hopefully this was somewhat fun, even though we're doing it from home, but hopefully you didn't miss the importance of what we're doing and why we're doing. All right, see you in a little bit.